Welcome back, folks. We're going to look at what might feel like some academic problems, and quite frankly, they kind of are, but I also think they're good practice. I wouldn't make you do them if I thought they were a waste of your time. I try not to waste your time as much as I can because I know that you've all got stuff going on in life as well. I try to be respectful of your time as much as you're respectful of mine. So thank you for that. Anyhow, so this might feel like an academic problem, but I think it's worthwhile because it gets some practice, and it gets some practice in recognizing when things are in series, when they're in parallel, when they're neither, when they're both, how we can combine them to reduce a circuit in complexity. So maybe we have a big complex circuit, but we notice a couple little things. We can make some combinations, and we can make a simpler circuit so that we can perform circuit analysis on it faster, more consistently, get the right answer a little more confidently. But we have to be able to identify these connections. Okay, so a lot of times we'll find problems like these in textbooks or on your web work and on the exam and things like that. You're not getting away from it. And it's really testing whether you understand series, parallel, neither, and both. How many times can I repeat that for you? I'm trying to repeat it so it gets stuck in your head. Anyhow, so we'll see a problem like this. Oh, no, you won't see a problem like this. Ready? You'll see a problem like this. There we go. And it'll simply state that we want to get all of these resistors, this network of resistors, down into a single resistor. So that if I put a voltage supply between A and B on this circuit, or if I put a voltage supply between the equivalent single resistor, the same current's going to flow. The voltage supply is not going to know the difference. Okay, it's going to have the same resistance. So how do we reduce this circuit to an individual resistor? And we're going to do that. In this case, I'll show you a trick how to do it later in the semester. It's a good way to do it, but you need some more sophisticated analysis methods. But in this case, we're going to say what's in series, what's in parallel, and can we combine them? So we usually do this as an exercise in class. It's hard talking to the camera. So I would usually say what's in series, what's in parallel. Hopefully you're looking at it and asking yourself that question while I'm talking to give you time to look at it and ask yourself that question. And the first thing that I notice, since this is our first problem, I threw some softballs at you. The first thing I notice is that these two are connected, okay, and they share this node up here, and they're also connected to the node down here, this big node A down here. So since they share the same two nodes, they are, in fact, in parallel. Okay, and since they're in parallel, we can say 4 ohms, and here's a little bit of notation for you. Sometimes you'll see it drawn as 2 pipes in parallel. 4 in parallel with 4. We can do it 2 ways, right? We can say 4 times 4 over 4 plus 4. Okay, that's going to be 16 over 8, also known as 2 ohms. That would be one way we can do it. That's the product over sum form. The other way we can calculate that is 1 over 4 plus 1 over 4. So that's a quarter plus a quarter. That's a half in the denominator. Invert a half, and you also end up with 2 ohms. Since there's only 2 resistors in this case, we can use either form to calculate the parallel resistance. Okay, so they're definitely in parallel. We know the resistance. The other thing that's neat about that, since there's 2 of them and they have the same value and they're in parallel, then we know that the combination is just going to be half. And that's always going to work out. If there's 2 and they have the same value, cut the value in half. Okay? If there's 3 and all 3 have the same value, cut the value in 3. Okay? So half of 4 is 2. So it works out in that respect as well. Okay. So great, we can combine them. What do we do with the rest of the circuit? Now all of this becomes an exercise in redrawing the circuit over and over again. Luckily I can just cut and paste the circuit to my heart's content. Okay, maybe get rid of that. And what I'm going to do is grab an eraser, and I'm going to erase those 2 all together. Okay, you might need to draw from scratch, but I have the magic of a digital pad here. Okay. I get rid of those. I removed the two that I was combining. And I know that the combination of the two is a 2 ohm resistor. Okay, that's good. So let's grab, I'll grab white again, and a pen, and I'm going to connect that 2 ohm resistor to the same two nodes. Okay, so let's scroll back up. So both of the 4s were connected to the node on the right of this 2 ohm, and they were both connected to A. So the equivalent resistor is going to get redrawn, and it's going to get connected to the node on the right of that 2 ohm, and it's going to get connected to A. Okay, and that was 4 in parallel with 4, and that was 2 ohms. And now that's my equivalent circuit. Now it's a little smaller, but my goal is to get it down to 1 resistor. But this is how we practice. Okay, so looking at the circuit again, we want to say what's in series and what's in parallel. Well, this is where I catch some people, and I love when I catch you in class, because then I know that I'm not going to catch you on the exam, right? So some people will go, oh, the 6 and the 2 are in parallel, and if I could virtually throw something at you, because that's wrong, I would, but luckily you're behind the camera. They are geometrically in parallel, but they're not electrically in parallel. They would have to share the same two nodes. The 6 is connected here, and this 2 ohm that we just drew over here is connected over here. They're two different nodes, so they don't share the same two nodes. They're not in parallel. The ones that I see that can be combined, and hopefully you've seen it already, it's a little easier to see, I think. Maybe you disagree, and that's okay, is this 2 ohm up here and this 2 ohm down here share this node, and they share it exclusively. So those two are in series. Okay, so I'm going to play the same game again where, well, let's mark that so that you have some record of why we're doing this. These are in series. Okay, and well, oh boy, let's see. I thought I was being all slick with my nice digital pad here, huh? There we go. So we take the same circuit and we redraw it, and we erase those things. Okay, it's going to take me a little bit of work to erase them. Come on. Trying to do it a little faster than if I erased it all by hand. Come on, my hotkeys aren't working. There we go. Okay, so I got rid of those two. The rest of the circuit, all the rest of the circuit stayed the same. And let's see. So I'm going to combine those two, and I will correctly combine them to say that 2 ohms, since they're in series, plus 2 ohms is 4 ohms. Yes, in your college education, you are paying for me to teach you that 2 ohms plus 2 ohms is 4 ohms. There's a reason. But 2 plus 2 equals 4. Still equals 4. Didn't get away from that. All right. So we're going to connect up that series combination. We've made them into one equivalent resistor. And we're going to connect it here between the 5 and the 6. And we're going to connect it down here on A. Okay, so that's going to come out here. See, and as you get further and further along, this is 2 plus 2 equals 4 ohms. Okay, so when they're in series, we use plus. When they're in parallel, they use these pipes. As we get further along, I'm hoping it's getting easier for you to see what is in series and what is in parallel. All right, looking at this circuit, this newly drawn circuit down here, which I'm going to copy right now so that we have it. What's in series and what's in parallel. So hopefully by now you're looking at the 6 and the 4 and you say, okay, they're connected here and they're connected down here. So there's nothing in between them, right? So they are connected to the same two nodes. Because they're connected to the same two nodes, they're electrically in parallel. All right, so 6, we got white now. 6 in parallel with 4 is equal to, well, there's only 2, so let's do product over sum. 6 times 4 over 6 plus 4, so that looks like 24 over 10, or 2.4 ohms. Okay. So we can combine those, and we can make a 2.4 ohm resistor. All right. Anytime you combine, let's go with combine. Anytime you combine two resistors in parallel, the equivalent resistance is always going to be lower than the smaller value. That's because you're adding an additional path for current to conduct. And anytime you create another road, you're going to make it easier for cars to drive down that road. Okay? It's not like you're going to create another road and magically there's going to be a lot more traffic, unless you live in Hartford. Can't figure that one out. So it's always going to get easier, and because it always gets easier, the equivalent resistance is always going to be lower than the smaller of the values. So this one's 4 and this one's 6. Okay, so it's going to be lower than 4. Okay, and this is one of those gut checks that I do to make sure I did the calculation right. 2.4 is less than 4. If this was 4 and this was 4, it would be 2, right? But this is a little higher than 4. So it's going to be a little more than 2. So these are kind of the little mind games that I play, and I go 2.4. Sounds like a reasonable value to me. Okay, so 2.4, I combine those two. We redraw the circuit. We erase the two that we've combined. This is getting a bit silly, isn't it? Come on. Selection tool is a little finicky, apparently. There we go. There's not much left in the circuit. There's only a 5 ohm. And we say, okay, the 6 and the 4 were connected to the right side of the 5 ohm, and they were connected to A. And that's where we're going to draw the parallel combination here. Okay, so this is 6 in parallel with 4, and that's equal to 2.4 ohms. There's a point in there. Okay, last one. Just beating a dead horse here, right? What's in series and what's in parallel? Hopefully by now you can see that they are in series, and that they are connected here. They're the only two resistors left, so and they are correctly connected in series. Okay, so let's write that here. So these two, okay, these two are in series. Okay, so since they are in series, we can say 5 ohms plus 2.4 ohms is equal to 7.4 ohms. All right. I guess we're not redrawing that circuit. Let's just grab these two. Erase the 2. Come on. Erase the 2. Hey, look, they're gone. And consider where they were connected. So they were connected to B and they were connected to A. This node disappears when you squish them together. That could be a problem for analysis, but sometimes it's a good problem. How about we draw the resistor along with it? There we go. Okay, this was 5 ohms in series with 2.4 ohms, and that's 7.4 ohms. All right, we got it down to a single resistor. I'm going to have you do some of these in web work. All right, it's not going to hold your hand through it. It's just going to ask you for the answer at the end. But I do encourage you to redraw the circuit as many times as you need to, walk through these steps, and always ask yourself the question, are they in series? Are they in parallel? Before you do the combination. If you do it without asking yourself those questions, I'm afraid you're going to make a mistake, and I don't want you to do that. I want you to get the right answer, and I want you to get the right answer all the time. All right? It's a good goal to have. All right, we're going to do another one. I'm going to do that in a separate video, and these get more complicated. This was a first look, but it's good practice. Okay, series, parallel, neither, both. Stay tuned and good luck.